So I put together a little EGA graphics demo using Borland Turbo C++. And before I get into like how it works and what the code looks like, let's just look at the demo. You can see it here in DOSBox. So we've got some controls, and what we're a little red ball. And there's a bunch of white and gray balls just bouncing all over the place. I can bounce off the walls, and it's cute. You know, it's not the groundbreaking gameplay you might expect, but whatever. Okay, basic little thing. So let's look at how it works. There's a bunch of these data structures. Essentially, the important thing to understand is that every circle that you saw on screen there is what's called a DWG, or a drawing in this code. And drawings have some position information, some velocity information, color, and then functions associated with them that calculate the physics update and calculate the draw operation. Perform the draw operation, I should say. So for the player's physics, when he hits the ground after a jump, his y velocity vector is zeroed. And that means that he doesn't bounce. He jumps and he lands and he stops. And when he hits a wall, his velocity vector is reduced to 60%, 0.6 f. F just means the floating point number, not a double precision number. Not important, but when you see the F, it's still a number. Don't worry about the F. All the gray and white balls have this physics update operation instead, phys bouncy, which is essentially the same, except that when they hit a wall or the ground, I just invert the magnitude of their velocity vector in that direction. So if they hit the ground, then they get the same velocity they had as they hit the ground, but going up. You know, if they hit a wall, they bounce off with the same intensity that they hit the wall in the opposite direction. So they maintain constant velocity as they bounce around. It's a lossless bounce. We see the circle draw. Circle draw is fundamentally pretty simple. We set the color to the color, and we draw the circle. And so what I'm doing, right, I create a bunch of these. There's 20 of them. These balls, 50-50 chance that they'll either be the default color, which is white, or light gray. And we just go through, right? So we got a keyboard update handler. If a key comes in, W, we just add 5 Y velocity. That's how he jumps. And left and right, we just add some left and right velocity on A and D. S is a stop, so it prevents you from sliding any further. Man, wouldn't it be funny if the stop also zeroed your Y velocity? Why not? We'll just fucking do that too. Oh, and this is cool, so we'll see that in a second, the E key. But essentially all I'm doing, right, is we go through this linked list of objects, and we do all the physics updates, and then we do all the draw operations. So we go through the whole list, and we just say, okay, get me the current position's data object, which is a drawing physics function, and then just call that and pass in the drawing data. That's the important thing to remember too. These are not real objects. This is an object-oriented design. So the physics update and the draw update function take as a parameter the first argument, the actual data object update. So I have to pass it in every time. It's a minor inconvenience. It looks kind of ugly, but whatever. So we do that. We call the physics update, and then we call the draws. And what I'm doing here, clear device is just this flag I set up. So if clear device is enabled, then the screen flickers to black before we draw. If it's not, then we just draw on top of the previous frame, which you'll see in a second causes some trails. And here's the draw. It's the same thing. Current iterator position, get the object data, the drawing, get the draw function, and then draw it for the current drawing. And that's it. That's the whole program. There's really not that much to it. And we'll run it, and you can see. So the change I just made, before I could hit S and it would stop him horizontally and he'd fall straight down. But now I hit S and it stops him wherever he is. But then you can see the acceleration as he comes to the ground. So that's the reason this looks kind of okay. Things don't fall at a constant velocity. They move in arcs, just like the real world. You know, gravity has an accelerative effect, not a constant velocity effect. And if we turn off that that clear draw option, you can see, oh god, oh boy. Everywhere circle bounces, everywhere we draw it, there it is. We can turn it on and off on a whim. But and that's it. So these are EGA graphics. This is 16 color mode. It's 640 by 200 pixels. It's a low resolution EGA graphics. There's a high resolution mode that's 640 by 350, I think. But there's some additional limitations with that, down to memory pages associated. So essentially, in low color mode like this, you have effectively 4 screens you can draw to, and then you can flip between them, which could be used to eliminate this disgusting blur that you're seeing, where everything's all fucking cut up. I'm not doing that. I'm not doing buffered multi-rendering or anything. But in high resolution mode, you only have 2 pages. 2 pages is still enough, but 4 pages is better. You know, because you can have additional scenes all already drawn in memory and flip between them quickly, and it looks good. But anyway, EGA graphics in DOS, Turbo C++, cool. Thanks for checking it out.